All right, let's dive in. Deep, deep beneath our feet, there's this incredible force at work, constantly melting solid rock into a thick, gooey substance we call magma. So in this explainer, we're going to find out what happens when that magma decides it's time to take a little trip to the surface.
Because you see, that trip can end in two completely different ways. I mean, have you ever wondered why some volcanoes give us these beautiful, slow-moving rivers of lava, while others just detonate with the force of a bomb? Well, that, right there, is the big mystery we're going to solve today.
So here's our game plan. We're going to start where magma is born. Then we'll travel with it on its journey upwards, figure out the one crucial thing that decides its personality, and finally, we'll see the two very different ways it can show up at the surface.
To get to the bottom of this mystery, we've got to go right back to the beginning. Our story starts deep inside the Earth, kind of like in the planet's engine room. Okay, first up, a quick but really important vocabulary check. As long as this molten rock is hanging out underground, we call it magma. But the second it bursts through to the surface, it gets a new name, lava. Simple, right? But trust me, it's a key distinction for what's coming next.
So how in the world do you melt solid rock? It's not as easy as just cranking up the heat. According to the National Park Service, it mostly happens in two ways. One is when hot material from the mantle rises up, the pressure drops, and it just starts to melt. But the second way, and this is the one you see all around the Pacific's Ring of Fire, is a whole different ballgame.
And this breaks that second method down perfectly. It all kicks off when one tectonic plate literally dives under another one. As that sinking plate goes deeper, it gets hotter and releases trapped water. It basically starts to sweat. That water then rises up into the super hot mantle rock above it and acts kind of like salt on an icy road, dropping the rock's melting point like crazy. And boom, just like that, you've got magma.
So, now our magma is born, and because it's less dense than all the solid rock around it, there's really only one direction to go, up. So let's hop on the magma elevator and start the incredible ride to the surface. Down here, where we're starting this journey, maybe 50 miles deep, the conditions are just insane. The U.S. Geological Survey says the pressure is about 2.5 gigapascals. To put that in perspective for you, that is 25,000 times the air pressure you're feeling right now. It's so intense it keeps solid rock flowing like it's warm taffy. But as our magma elevator starts to go up, that crushing, unbelievable pressure starts to drop off. And it drops off fast. And this is the single most important thing that happens on this entire trip. It kicks off a process that honestly is going to sound super familiar. In fact, you've probably seen it happen 1,000 times. It's almost exactly like cracking open a can of soda. I mean, think about it. Inside that sealed can, all that carbon dioxide gas is dissolved in the liquid because it's under high pressure. You pop the top, you release the pressure, and poof, bubbles everywhere. Well, it's the exact same thing with our rising magma. Gases that were totally dissolved under that crazy pressure start to come out and form bubbles. And these bubbles, they are the key to everything that's about to happen.
But here's where the story can go in two totally different directions. The fate of those bubbles, and whether the ending is calm or incredibly violent, it all depends on the kind of magma they're trapped inside of. It all comes down to the magma itself.
So, the crucial point, the big takeaway, is this. A volcano's whole personality is decided by what its magma is made of. And specifically, it's all about one key ingredient, silica. The more silica you have, the thicker and stickier the magma gets. And this slide right here, this explains it all. On the left, you've got thin, runny, low silica magma. Think of it like warm honey. The gas bubbles can just rise up and escape pretty easily so you don't get a big pressure buildup. That leads to what we call an effusive eruption, basically a gentle flow. But on the right, that's your thick, sticky, high silica magma. This is more like cold peanut butter. Those gas bubbles get trapped. They can't go anywhere. So the pressure just builds and builds and builds until it leads to a massively explosive eruption. So let's take a look at what these two very different eruption styles actually look like when our magma elevator finally dings at the top floor, the Earth's surface. Okay, first up, the fate of our thin, runny magma. This gives you an effusive eruption. The gases get out gently, creating these spectacular, gusher-like fire fountains. This makes superfluid lava that creates those iconic red-hot rivers of rock we all imagine. And while they're definitely destructive, they're usually pretty slow-moving and predictable, which, as the USGS notes, means they rarely threaten human life directly. If you want to picture this, just think of Hawaii. Those huge shield volcanoes like Kilauea and Mauna Loa are the absolute poster children for these incredible, but relatively peaceful eruptions.
But now for the other side of the coin. With that thick, sticky, high silica magma, those trapped gases build up to an unbearable pressure until, bam, the rock just can't hold them in anymore. The magma doesn't flow out, it blasts out, shattering into millions of pieces called tephra and creating these terrifying, super-fast clouds of hot ash and gas.
The famous 1980 eruption of Mount St. Helens in Washington is just a chilling reminder of this kind of destructive power. It wasn't a gentle flow, it was a devastating blast that literally blew the top off the mountain.
And this is why that difference is so important. The dangers from an explosive eruption are just immense and deadly. Tephra isn't just a bit of dust. It can be anything from tiny ash particles to boulders the size of a house. Ash clouds can ground airplanes and suffocate everything for hundreds of miles. And the most dangerous of all are pyroclastic flows. Think fiery avalanches of hot gas and rock moving at hurricane speeds, and lahars, which are these destructive volcanic mud flows that can just bury entire towns.
So after our whole journey, from deep in the Earth's mantle all the way up to the surface, it really all boils down to one surprisingly simple idea. A volcano's personality, whether it's a gentle giant or a violent destroyer, is all controlled by how easily gas can escape its magma. It's all about the bubbles.
And the thing is, this process, it never, ever stops. Right now, deep beneath our feet, magma is forming and starting that slow climb upwards. The magma elevator is always running. The only question is, where on Earth is it going to open its doors next?